In Unit 1, we talked about fossil fuel sources and uses globally. In Unit 2, we're going to talk about the environmental impacts of fossil fuel combustion, primarily air pollution and global climate change. So today we start with air pollution. So the World Health Organization estimates that about 3 million people per year die prematurely because of air pollution. In the US, about 70,000 die prematurely every year, primarily from vehicle emissions. In the state of California, they estimate that they spend $200 million annually on medical costs associated with air pollution. So what pollutants are made when we combust fossil fuels? Coal is made up primarily of carbon. So when we combust coal, which means to burn it at a high temperature with oxygen, we get carbon dioxide, which of course is a primary global climate change gas. Coal also has sulfur. So combusting coal, the sulfur also reacts with the oxygen to make SO2 and SO3 that we refer to as SOx. When we combust petroleum in vehicle engines, we get carbon dioxide again and water vapor, and the same thing for natural gas. We also get carbon monoxide, CO, and volatile organic compounds, VOCs. Because what we are combusting is air, and air is primarily nitrogen, about 79% nitrogen, 21% oxygen with some other trace substances. The nitrogen and the oxygen in air react at high combustion temperatures to make NOx, which is either NO2 or NO3. There's a few other trace elements in coal. The really important ones to think about are lead, because when coal with lead is burned, the lead escapes out the top of the power plant in the stack gases. It then falls back to Earth, and via precipitation often winds up in waterways. If people drink water with lead levels that are too high, it can be a neurotoxin and lead to motor development issues and brain function issues, especially in young children. Mercury and arsenic are also of concern because of their toxicity levels. Primarily when we combust coal, also we get particulate matter, which are particles that are on the order of microns in size. 1 micron is equal to 1/1000th of a millimeter. So things on that order are often so small that we can't even see them. Now there's some natural sources of particulates and aerosols, including erosion in farm fields or urban construction sites, my favorite, pollen, and active volcanoes, but primarily combustion of fossil fuels. And in recent years, in many places globally, forest fires. Of greatest concern is particulate matter less than 2.5 microns in size, otherwise known as PM2.5. Our body's natural defenses, the cilia in our nose that make us sneeze, cannot filter out particulate matter that small. So it lodges deeply in our lungs, causing respiratory diseases like emphysema and lung cancer, and heart and other cardiovascular diseases. Okay. Air pollution sources can either be stationary like a power plant or mobile like vehicles. Mobile sources are hard to control for because there are far, far more vehicles than there are individual power plants that are emitting pollutants. There are some natural sources, active volcanoes, biologic decay, forest fires, which again have gotten worse globally in the last 10 years because of climate change and ocean spray. But combustion of fossil fuels, it makes up about 99% of our air pollution. So let's talk a little bit about some of the primary pollutants and why they're of concern. Carbon monoxide primarily comes from auto engines. It builds up worse in heavy traffic, obviously, and in unventilated areas. So it's never a good idea to have your car engine on in a garage with the door closed. The reason for this is that at low levels, carbon monoxide causes dizziness and headaches. At high levels, it binds to hemoglobin in the blood, which means oxygen doesn't bind with hemoglobin, so it leads to suffocation and death at high enough exposure levels. Okay. SOx comes from primarily coal combustion and a little bit from diesel, and again 99% from coal combustion, maybe 1% or less from sea spray. It causes higher illness and death rates, especially respiratory diseases like lung cancer, emphysema, and bronchitis. It also participates in acid rain, we'll learn about that in a minute, and decreases crop yields in farmlands. Okay. Volatile organic compounds are those that are easily converted from a liquid form to a gas form. Main sources are petroleum, trash incineration, industrial solvents, and some biological decay. These cause reduced visibility, they damage plants, and as we'll talk about in a minute, they make photochemical smog. Okay. So, photochemical smog is a really big problem in big cities. If you've ever flown into Houston, Denver, or Los Angeles, you see a cloud of burnt orange, brown yuck hanging over the city. That's photochemical smog. It's created when NO2, which comes from vehicles, fossil fuel combustion, VOCs, the primary source is vehicles, react in the presence of sunlight. So sunlight is needed, and it makes ozone. Now, high up in the stratosphere, the ozone layer protects us from UV radiation. But down in the troposphere, the air that we breathe, it's an air pollutant. And it causes eye irritation, reduced visibility because of the brown cloud of yuck, and severe respiratory ailments, and it also damages plants. Now, in some parts of our country, rural areas where hydraulic fracturing is occurring, because methane is a VOC, we're seeing photochemical smog levels in those rural areas where fracking is happening almost to the same degree that we're seeing in big cities. And this is resulting in loss of crop productivity in those areas. Okay. Okay. Acid rain has been a problem since the early 1900s. When we combust coal for energy, again, we make SOx that leaves the top of stacks and travels long ways in the air downwind. While it's doing that, it reacts with water in the atmosphere and makes sulfuric acid. NOx also reacts with the hydroxyl radical to make nitric acid. NOx and SOx are the two primary precursors to acid rain. To a lesser degree, CO2 reacts with water vapor to make carbonic acid, but it's not as potent an acid. Areas like the far northeastern United States into Canada, downwind of industrial areas, and across Europe and Scandinavia have seen a lot of damage from acid rain. You get loss of native fish populations because some fish are very sensitive to pH levels and cannot survive in acidified waters. It also damages fish gills, which is how fish breathe. So if you can't breathe properly, the fish are going to be compromised, and it damages their ability to reproduce. It also damages aquatic plants. So aquatic plants cannot live in acidified water either, and the smallest fish rely on aquatic plants as a food source. So acid rain disrupts the fundamental food chain in a lake. You'll see up in the New England area acidified lakes that look pristine, but that's because there's no fish or plant life in them, so the water looks very clear. They're probably lakes that suffer from acid rain. It also damages terrestrial plants. So across these same areas of New England and into Canada and across Scandinavia and parts of Europe, many forests have been permanently damaged by acid rain because it burns the leaf of the plant in much the same way that dropping acid on your skin is going to give you a pretty severe burn. In addition, it damages limestone statues and buildings. This is a concern just for the integrity of buildings, but it's really of grave concern in places like Italy and Greece that are seeing statues that were part of, great antiquities that have been there for hundreds of years displayed out in the open, now being damaged by acid rain. Okay. Now, in the United States, to combat poor air quality, the U.S. EPA, Environmental Protection Agency, identified 6 chemicals as being criteria air pollutants: SOx, NOx, particulate matter, carbon monoxide, ozone, and lead. And note that carbon dioxide is not on that list, and we'll talk about that in our next section. The EPA established national ambient air quality standards for 2 different standards. Primary standards protect human health. So what level of carbon monoxide can people be exposed to for a given amount of time before negative health impacts are observed? Secondary standards protect human welfare. So things that might reduce crop productivity or damage buildings, or if you live in an area with photochemical smog, it degrades synthetic rubber materials, so you're going to have to replace the tires on your car more frequently. Okay. The problem with the National Ambient Air Quality Standards is it's hard to enforce them. So about the only way to do this is to designate a highly polluted area as a non-attainment zone. What that means is that industries are limited in whether or not they can expand. They have to reduce their permitted amount of emissions in one area to expand and have additional emissions from another area. If they're unable to do that, then they can't grow. You also, if you live in a non-attainment area, have to pay more money for reformulated gasoline. So being designated a non-attainment area is really bad for a local economy. Right now, though, about 100 million Americans live in counties that fail to meet at least one standard, and sometimes that includes Brown County, where we live. So, in order to combat the problem with the Clean Air Act, we started moving in the right direction to control emissions. So since many emissions come from vehicles, there's new emission controls, not new to you, but new since the 1970s, to reduce VOCs, carbon monoxide, and NOx. So vapor recovery systems and recirculation of exhaust streams help save fuel by recirculating unburned fuel back into the engine. Catalytic converters reduce carbon monoxide and reduce NOx, so that helps solve the problem of photochemical smog. They also cannot run with leaded gasoline, so now you can only buy unleaded gasoline, which reduces the amount of lead being released in the environment. With cleaner burning fuels, then, since the 1970s, the United States has seen a 90% reduction in vehicle emissions. Okay. Coal is a big problem. Coal is the dirtiest fossil fuel to burn. So there's a couple of solutions. Burning low sulfur coal has resulted in a shift from coal mining in Appalachia, where they have high sulfur coal, to western Rocky Mountain, Montana, Wyoming mining for lower sulfur coal. The most prevalent technology used on this list is number 3, removing SOx particles after combustion. That's the most efficient way to do this. Fracking has led to shift away from coal in the United States towards natural gas, because natural gas now costs less than coal, and it also burns cleaner. Number 5 is not very practical, because if you send things through a tall stack, all you're doing is blowing your pollution problem downwind to somebody else. So to remove SOx, all modern coal plants in the Western world have scrubbers. The fancy word for that is flue gas desulfurization. Here you have something like calcium carbonate dissolved in water. You bubble the effluent gas up through that water. The SOx in the effluent gas reacts with the calcium carbonate to make calcium sulfate, which stays in the dissolved water. So this has largely solved the problem of acid precipitation in the Western world. But it does create enormous amounts of waste sludge, and the price of electricity went up when this technology began to be implemented. Okay. Particulate matter is removed from electrical power plants by either bag houses, which are fairly simple to operate. It's basically a multi-layer cloth filter, much in the same way that we wear masks to protect ourselves from the COVID virus. And the airstream has to pass through this multi-layer fabric filter. It's very effective in removing particulate matter. Scrubbers also do a pretty good job. So where you're already using scrubbers to reduce SOx, you're doing a pretty good job with particulate removal. Electrostatic precipitators are technologically interesting, but not nearly as effective. Okay. So these are some of the ways that we've made air quality better in the United States and across the Western world. In our next lecture, we're going to talk about global climate change.